So basically in the lab 6 of 533 we have a lab where we need to make a pipeline data path on NetFPGA. So at first the part 1 is about extending and synchronous adder into ALU. So at first we have created an 32-bit adder. Using that adder we need to make that particular adder to 64-bit, and then by using ALU we need to implement various functions. So there are various functions which have been given to us as well, which we need to implement. That is add, subtract bitwise, and bitwise or bitwise XOR, compare, and logical shift functions. And basically this is an ALU control signal which will be used to select which of the operations should be performed, and there is a overflow flag. So this overflow flag is used when we are doing the subtraction, and basically if the result is not same then we go with the overflow flag. So this is how it is. So I will show you how the part 1 is done. So I will just show you through the okay. So this is the simulation of it, and this is the top level design of the ALU part. So in the top level design, what I have done is, so basically there were two approaches that we can use. It's either Verilog code or by using structural schematic method, that is by making one by one component and going to the hierarchy. So I have used the schematic method. So in here you can see that at first I have created an adder component, and later on to make this adder compatible to subtractor, I have also made a XOR as well, 64-bit XOR, so that the bits of B gets inverted and so that it will be fed to B. And we know that whenever adder and subtractor is used, then we use a XOR gate. So whenever it's 0, that is sub signal is 0, we say that it will be an addition, and so the cout will be carried forward, or else it will be XOR with the sub value which will be 1 when in case of subtraction. In the same way we have also designed the overflow logic as well. So here you can see that we have a overflow logic where we usually take the inputs and the inputs of C31, the input of 63rd bit, B of 63rd bit, and that of carry out as well, and accordingly we calculate the overflow flag as well. So overflow is named as OF out here in here. So apart from the added and subtractor, we have a bitwise AND operator, then XOR operator, then OR, compare, and bit shift register. And basically in total, to select anyone from the above, we have created an 8:1 mux. So basically ALU control signal is fed through that, and accordingly we'll be getting an Y out. So I'll just go through the overall top level module as well. So this is the adder module that we see in the top phase. So this is adder, and inside that there will be a 4-bit adder. Inside that it will be 1-bit adder. It will be same for XOR as well. So this is the 16-bit XOR to 16-bit XOR which have been taken, and so on. So in this way we have designed a particular ALU. And now when it comes to test bench, we have given the inputs to the test bench. So I will just show you. So for instance, for random I have given a particular test bench, that is, suppose we are giving 2. Suppose we are giving value as 2. So basically if you see at the top level of our design, so whenever it is 2, 2 is nothing but it is connected to it is connected to the 64-bit and bitwise, that is and bitwise. So accordingly we'll be getting output. So at first I have given the inputs through here. So basically I have given down the input, that is FFF00 and so on, and this is the value of B as well, and control signal is given, and now we'll be checking what will be the output. So this is the simulation that I have run. So basically this is the output that we get to observe. So I have also cross-checked the values as well. So this is how it goes. A value is fed, B value is fed, and later on according to the ALU control will be given. Also I am generating a compare signal as well. So as compare signal is 1 bit, instead of feeding it to 64-bit, I have been having the compare signal a different signal, 1-bit signal. So here you can see that once the input is given, it is going to low, which means that the two data input that is given are not equal. And initially you can see it is high because both the inputs were initialized to 0, so because of which it was high. So this was the first part of our lab. So basically going towards the second lab, in the second part of the lab we were asked to build register file and memories. So what we did, instead of showing means we don't need to include the simulation waveforms and all the stuff for this part 2 part, but basically I will just explain what we did. So basically we created a register file, so by using a Verilog code, and later on we created a BRAM, that is one for memory data, one for data memory and one for instruction memory, and accordingly we have created it. So this was about part 2. So now this is something that it is important, that is the part 3. So in the part 3 what we need to do is we need to design a pipeline. So basically first we have a PC counter goes to the instruction memory, then according to the address of PC we'll be fetching out the instruction. This will be given to the first stage, that is IFIDA register. From there we have a register file in it. So basically that particular instruction will be decoded in such a way that register 1, register 2, write address 1, W data will be given, and accordingly R1 out and R2 out, which is of 64-bit each, will be created. In the same way we have a second, that is decode and execute stage register. And we know that we are not, for this particular example we are not implementing any ALU for this particular lab, so we are not giving anything, and we are just forwarding the signal from one register to another register. And at the end we have a data memory. So basically this, there was some instruction which was given to us, so we can say that here load address, that is load instruction, store instruction, were the two instructions that we need to add accordingly. So basically we have data memory, so that we'll be fetching the data for from a particular address, and we'll be storing that into a register file. So this was about the pipeline. So we have designed a pipeline as well. So basically this was the instruction format which was given to us. So the 30, so it's according to us which particular bit should be what it should be behaving. So this is the data memory which was asked us to initialize, and this was the instruction memory. So basically what we do is we force the value into the data memory and the instruction memory, and later, so these were the values which was first fed to instruction memory as well as data memory, and later on we started the execution phase where PC was incremented sequentially. And as the PC incremented, suppose PC equals 0, this particular instruction, that is load instruction, will be added, second one also load will be added, and so on, and at the end store. So basically main purpose of this particular app or this particular part is to verify whether in the store operation are we getting the value stored in the register file or not, and in the location 3. So this is the main motive of this particular lab. So I will just walk you through with the so this is the ALU. So basically this is the pipeline that we have made. So I'll just go through the pipeline code as well. So here you can see that these are the various signals which are being provided. So basically this is the signals which are being provided through which we will be writing into the instruction memory and data memory to initialize the particular thing. So these are the registers that we'll be using here, IFID and IDX and so on. And basically we have instantiated all the three designs, that hey, instruction memory, register file and data memory, and accordingly we have attached the signal. One thing to note is that the register file will be always getting the right address, the right enable signal, and the data out from the EXW stage, because of which we have instantiated in here. And accordingly I have written down the FSM for a particular block. So basically the first FSM is about initialization, that is if reset then we need to initialize all the state by 0. Later on this is the instruction write, where we'll be writing into the instruction memory. This particular thing will be writing into the data memory, and the last one is nothing but the execution phase, where it will go into a continuous loop, and as the PC increments it will perform the following functions which were asked and explained before. So I will just simulate this particular thing. I will just close it, this particular simulation. Okay, and I will just run this particular simulation. Okay, so this is the particular output I will be getting. So I will just walk you through what is the input. So basically I will just explain the waveforms that we are getting. So initially what we did is, initially first we initialize the instruction memory and data memory. So in here you can see that, okay, yeah, so in here you can see that in address 0 this particular address was stored in the instruction memory, and then 01 this particular, and so on, was given to this particular first. So instruction, first 4 instruction was so that it was provided to us, that is this particular instruction. So this was the first 5 instruction which was provided to us. Later the data memory was initialized. So you can see here, where is data, okay, instruction memory, and here data memory. So in the data memory first we were asked to write anything inside the particular file, so it is 0. So in the 0th location this particular value was written, and so on for the particular. So now the thing is, after our FSM goes to a particular stage, that is this particular state. So after writing into the instruction memory and data memory, we go in this particular state where we'll be executing. So if we can see in here that as the PC goes, so here you can see that, okay. So first in PC is given as 0. So we know that the PC was nothing but the address which will be pointed to the instruction memory, and the instruction will be going to get fetched, right? So first, as PC is equals to 0, you can see that this particular data, that is Okay, so basically we have also created a temp variable as well to know how the signal flows, right? So basically here you can see that at 0 this particular data is loaded, for 1 it is this is the particular data, and so on, and it goes through the 4 instruction that we are going giving in the test bench. And you can see that at the end of the pipeline, what our main goal was to do the store operation. So I'll just walk you through. So you can see that at particular three address, so 0 1 2 3 third location, we need to store the value which has been given in this 2. So basically in the 2, by using the load operation, we have already stored 4 value in this particular value, and then we are expecting value of 4 in this particular register, right? So basically we will just see whether the register file gets updated or not with that particular value, and this is the particular output for this register file. And you can see that, yeah, so in here you can see that register file is been getting 4. So this is how the lab was performed, the part 3 of the lab, where this particular pipeline functionality was being tested. And when it comes to the last part, that is integrating the pipeline into NetFPGA, we are working on this particular thing. So basically we have made our own user data path, and we have also editing the IDS rec file as well. So we have been getting some kind of errors. So we are planning to finish it by today or tomorrow morning itself. So part 4 is the one which is remaining for us, and rest of the things are complete. Thank you.